We're going to talk about imaginary numbers, and if you understand imaginary numbers, you're going to get this joke. And the 2 and the 3 are kind of hanging out. Number 8 says, "Hey, you guys, want to meet my new friend?" And the number 3 says, "Sure, but where is he?" Number 8 says, "He's right here." And they look over, and number 8 says, "Why can't anyone else see you?" And the square root of -1 says, "Beats me," because the square root of -1 is actually imaginary. So here's the square root of a negative real number. For any positive real number a, the square root of -a is actually equal to I square root a, I standing for imaginary. In this example, you can see the square root of -4 is equal to I square root 4. That I tells you that there was a negative inside the square root, or the radical. And so you take the square root of 4, which gives you 2. Then I multiply I times 2, and I rewrite it as if there were a variable there with a coefficient. So it would really be read 2I. It also says that we talked about, note that the square root of -4 squared is equal to I times the square root of 4 squared, which is equal to I squared, times the square root of 4 squared. And we're going to talk about what I squared is later, but you can see here that I squared is equal to -1 times 4, and so it's equal to -4. So you notice that it is not a positive 4. That's a note that we'll end up exploring a little bit more in this chapter. So let's simplify it using this property. Letter A says square root of -2. Again, that negative just means that I need to pull it out of that square root. Therefore, that negative gets pulled out as an I. The square root of 2 gets left. So when I rewrite that as a positive, it just becomes I square root 2. Back to -12, I pull that I out, so now I've got I square root 12. And back to our review from algebra that I had you do a couple of days ago. You have to simplify the square root of 12 as well. And that can be rewritten as 4 times 3. The reason that I chose 4 instead of 6 and 2 is because 4 is a perfect square. And I can take the square root of 4, so it becomes 2I times the square root of 3. And that's the most simplified version. Letter C, pull that negative out, so I get I square root 36. And the square root of 36 is 6. So that answer is 6I. When we look at these, we call these numbers complex numbers. A complex number have a real part and an imaginary part, and they're formed by an addition sign. Yes, you can have a negative sign as well. A complex number can be written in the form of a plus bi, where a and b are real numbers, and they do include 0. Now, as you look at the complex numbers are consisting of real numbers and imaginary numbers. So the real numbers, I'm going to outline those in a red. These are all of the types of numbers that you knew before this chapter. And today, we are going to add imaginary numbers. And that together, the real numbers and imaginary numbers as a combination, create the complex numbers. So the complex numbers do include all of the real numbers, all of the irrational numbers, all of the rational numbers, everything that you see there in that red box, as well as adding now to that the imaginary numbers. So we're going to rewrite the square root of -18 plus 7 in the form of a plus bi. So I'm going to rewrite the square root of -18. The square root of -18 is I square root 18. Have that plus 7 there. And I can rewrite the square root of 18 as a perfect square of 9 times 2, which tells me that the square root of 9 is 3. Still have the I square root 2 plus 7. Now notice that in this form, the imaginary number comes second. So when I rewrite it, I'm going to write it as 7 plus 3I square root 2. Now, finding the absolute value of a complex number. There's a lot of stuff in this video, so you want to make sure that you're breaking it down. If you need to go back, please review. The absolute value of a complex number is given by this formula. You should write this formula down and make sure that you keep it in your notes. And then we're going to use that idea to figure out what the absolute values of these particular complex numbers are. In this case, this is your A, so A equals 6, and B, notice that B does not include the I. The I is next to it. So B is kind of like the coefficient of our imaginary number. It is a factor, but it's that number that's in front of the I. And so in this case, B here is -4. When I put that into this equation, that means the square root of A squared, which is 6, plus B squared, -4. I rewrite that as the square root of 36 plus 16 becomes the square root of 52. And now as I look at that, the square root of 52, I know that I can divide that by 4. And so I can rewrite that as the square root of 4 times 13. And I can take the square root of 4, which is 2, but the square root of 13 stays. So in the most simplified version, the absolute value of that complex number is equal to 2 square root 13. Now you're going to notice that the square root of A squared plus B squared kind of looks like a property that we've used before, the Pythagorean theorem. And it is based in that. In your book, you'll be able to see how they came up with that, but I will also talk about that when I return and we talk about this in class. So let's look at the next example, letter B. A here is -2, B is +5, so I'm going to take the square root of -2 squared plus 5 squared. So it's the square root of 4 plus 25, and that would just give us the square root of 29. 29 is a prime, so it is just left like that. That is the simplest version. In this case, A is 0. There is no real term. B, however, is 4. So when I take the absolute value of that, the square root of 0 squared plus 4 squared, this is the square root of 16, which is equal to 4. Additive inverses, probably the easiest thing that you will screw up the most. I know that sounds funny, but the additive inverse just means that you take the negative of each of those pieces, or the opposite of each of the parts. So the additive inverse of -5i is going to be positive 5i. The additive inverse of 4 minus 3i, again, it's taking the negative of each of the parts, so it's going to be -4 plus 3i. And letter C, a plus bi, -a minus bi. Again, a very simple idea, yet it's one of those things that we forget. And so you want to keep in mind, it just means the opposite. So the additive inverse is just the opposite. It just really means change the signs of everything. Simplifying each expression, you're going to simplify them just as if you were combining like terms. The imaginary numbers can be combined, and so can the real numbers. You still need to use a distributive property to distribute that negative. So this is really 8 plus 3i minus 2 minus 4i. I'm going to combine my 8 minus 2 to get 6. 3i minus 4i gives me -i. 6 minus I, or 6 minus 1i, is the answer for letter A. Letter B, again, that distributive property, so 7 minus 3 minus 2i. Combine the 7 minus 3, so it's 4 minus 2i. And lastly, these parentheses, the grouping is negligible. I don't need it. So I can just combine my 4 and combine that with -6i plus 3i, which gives me -3i. That is just combining like terms or simplifying the expressions. When you're multiplying, you're going to use the rules that we've done in the past as well. So 12 times 7, and 12 times 7 we know is 84, and we get I squared. Now we do need to talk a little bit about what is I squared going to equal. As you're looking at this, I'm going to give you a little chart. The square root of -1 is actually I. Now if I look at I squared, that means that I would take the square root of -1 times the square root of -1. Well, the square root of -1 times the square root of -1 breaks down to -1. If I looked at I cubed, that would mean the square root of -1 times the square root of -1 times the square root of -1, which would give you I. Again, you would end up with the first two terms giving you -1, and -1 times the square root of -1. -1, or the square root of -1 is I, and so it's I. And then I to the fourth power gets rewritten as -1 square root of -1 times the square root of -1 times the square root of -1, or -1 times -1, which is just 1. And then this repeats itself. I, -1, I, 1. And so I to the fifth would be I again. I to the sixth would be -1. I to the seventh would be I, and I to the eighth would be +1. So when I come back up to letter A here, I squared is equal to -1. So this is actually equal to -84 when I solve that. Letter B, in this case, use FOIL. 6 times 4 gives you 24. 6 times -3i is -18i. -5i times 4 gives me -20i. And then I end up with -5i times -15i, which gives me -5 times -3, which gives me plus 15i squared. So now I need to combine like terms, but I also need to convert that I squared. So I get 24 minus, I'm going to combine -18i minus 20i, get -38i. And then that I squared means -1, and -1 times 15 gives me a -15. Combining the 24 and the -15, I get 9 minus 38i. Let's do it again. Show you a second example of the same idea. 4 times 4 is 16. 4 times 3i gives me a positive 12i. -9 times 4 is -36i. And -9i plus 3i, or times 3i, will give me a -27i squared. Doing the same thing, I'm going to combine like terms and rewrite that I squared. 12i minus 36i gives me a -24i. But that I squared and 27 is going to change its sign to a positive 27. Now I take 16 plus 27, I get 43 minus 24i. The last thing we're going to do is solve some of these equations. We're going to use the square root method in each of these because there is no b term. So I'm going to solve by subtracting 48 on both sides. I end up with 3x squared equals a -48. I'm going to divide by 3. X squared is now going to equal 16. -16, sorry. Take the square root of both sides. And because it's a negative inside the parentheses, whenever I input that square root, it is going to be your plus or minus the square root of -16. And that negative comes out as an I, and the square root of 16 is 4. So this answer is going to be plus or minus 4i. Looking at letter B, we're going to add 150 to both sides. Negative 5x squared is equal to a positive 150. Divide by negative 5. So x is going to x squared, is going to equal a negative 30. Again, I'm going to take the square root of both sides, which gives me a plus and a minus square root. So I'm going to end up getting x is going to equal plus or minus the square root of 30. And the square root of 30 cannot be broken down any further than that, but the I can be taken out. So it's plus or minus I square root 30. And the last example, I'm going to subtract 2 again. 8x squared gives me negative 2. I'm going to divide by 8. I do want to keep this in fractional form. So I get x squared equals a negative 1/4. Noticing that 1 and 4 are perfect squares, that's going to be very nice in order to take the square root of that. So again, I'm going to take the square root of that, and in essence, I do have to put in that plus or minus. So x is going to equal plus or minus. The negative comes out as an I, and the square root of 1/4, I can take the square root of 1 and the square root of 4 to give me 1/2i. If you do end up with a square root in the denominator, you do have to rationalize the denominator. And we will talk about that a little bit more when I return to class as well. But in a nutshell, you really want to just multiply by whatever is in the denominator. If there is a square root of 2 in the denominator, you're going to multiply by the square root of 2 to rationalize it. And again, you do not want to have radicals in the denominator.